In this video, I want to talk about a very important application of Ampere's law, the solenoid. I'm going to first explain what a solenoid is, and then I'm going to show, using Ampere's law, that the magnitude of the B field inside a solenoid is given by this formula here, where mu naught is the permeability constant, n is the number of coil turns per unit length, and I is the electric current flowing through the wire. I'll then go through a basic example problem using this formula. So let's begin. A solenoid is essentially just a type of a coil of wire, kind of like this, shaped like a hollow cylinder with an electric current flowing through the wire. Now, as you might know, an electric current will generate a magnetic field around a wire, but if the wire is arranged like a coil, that field will be shaped in such a way that it looks like the magnetic field is flowing through the coil itself, as I've tried to show here. And it creates this interesting situation in which we have a very strong magnetic field flowing through the inside of the coil, while the part of the field that's some distance outside the coil is very weak. The word solenoid specifically refers to special cases of this, where the coil is tightly wound together, and the length of the solenoid is much greater than its diameter. In that case, we can usually ignore the outside field altogether, and assume that the inside field is uniform. So let's talk about how we can use Ampere's law to find out what the B field is through the solenoid. Let's first remind ourselves what Ampere's law actually says. Ampere's law is often written like this, and it tells us that if we have a closed loop, like a square, or a circle, or some other curve that connects back to itself and has no starting or ending point, then the total current flowing directly through that loop, multiplied by this constant, is equal to this dot product integral, which looks scary, but that's only because this is a very formal way of writing it. In practice, this usually just means the B field parallel to the loop, multiplied by the distance within the loop that it travels through, or B times S. So now it looks much nicer. So if we want to use Ampere's law on this problem, let's first choose a spot to draw a loop. I'm going to draw a rectangular loop like this right here, because here it's in a position where the current from the wire is flowing directly through it, and the loop itself is parallel to the direction of the B field. Because remember, the B field, the magnetic field, is flowing through the loop in a direction like this, where it's just completely parallel to the loop itself. I chose to draw it as a rectangle because either that or a square will make it easiest for us to do math using the various segments of the loop. I can label the segments by drawing little letters or some other label, like A, B, C, D, by all the vertices of the rectangle, so I can label each of the segments of the rectangle. Remember, this left-hand side of the Ampere's law equation refers to the components of the B field that are parallel with the loop itself. So let's see what this loop can tell us. Well, right off the bat, we can see that these two arms of the loop on the side can be ignored completely, since they're completely perpendicular to the B field. Remember, if the B field's going in this direction, then arms AD and CB are perpendicular to that. So none of this magnetic field are going to be along the direction of those segments. So they can be crossed out. This top arm can also be ignored since it's outside the coil, and as we established earlier, the magnetic field on the outside of a solenoid is negligible by definition. So the only section of the loop that we need to worry about is the length AB, the length that runs straight through the inside of the coil. If I define the length of section AB to be S, then the left-hand side of Ampere's law is simply just B times S. So that's the left-hand side of Ampere's law. And now let's look at the right-hand side of the law, which includes a variable for the total current enclosed within the loop, I sub ENC. So let's think about how we can describe the amount of current enclosed within the loop. Since the total current through the square loop increases based on how many turns of the coil are included in the rectangle, it will increase if we make the length s larger. So we can imagine that I ENC must be proportional to the length of s somehow. So we can say that the total enclosed current is equal to the current through the wire, which I'll say is I, times the number of coil turns within the rectangle, within the loop. And a clever little thing we can do is say that that number, the number of turns in the loop, is equal to n times s, where s is, of course, the horizontal length of the loop, but n, we can define n to be the number of turns of the coil per unit length. For example, if 1 meter of the solenoid contains 500 layers of the coil, then that solenoid's n value is 500 turns per meter. So going back to the Ampere's law formula we've been setting up, let's add that. Let's multiply our new little expression here, and don't forget to add the magnetic constant. So we've got the mu naught times I times ns, and now we can see that these s's will cancel out since they're on both sides. So we're now just left with a formula telling us that B is equal to mu naught times n times I. Now it's important to note you might also often see this formula written a little differently, maybe more like this: mu naught times I times capital N divided by L, where capital N is the total number of turns in the solenoid, and L is the total length of the solenoid. Both of these formulas say exactly the same thing, but the second version might be slightly more useful in problems where you aren't explicitly given the solenoid's number of turns per length directly, but you are given enough information to figure it out from some length and the total number of turns within that length. To hopefully make all of this more clear, let's go through a simple example problem. Let's say we have a solenoid that is 95 centimeters long, has a radius of 2 centimeters, and the solenoid has a winding of 1100 turns. It also has an electric current of 3.50 amperes flowing through the wire. And in this basic example problem, we want to find the magnitude of the B field inside the solenoid. So let's scroll up a little bit and look at the formula we have. So the formula we just derived using Ampere's law tells us that the B field is equal to the magnetic constant times N times I. But remember, we aren't given N in the problem, because remember, N refers to the number of windings per unit length of the solenoid. Now the problem doesn't give us that exactly, but it does give us enough to figure that out, because we're given the length of the solenoid and the number of turns it has. So in this context, small n is equal to big N over L, where big N is equal to the 1100 turns that were given, divided by the length, which is 95.0 centimeters. I'm going to rewrite this in meters to keep things in SI units. So that's going to be 1100 over 0.95 meters. And now we can try plugging this into our formula here. So B is equal to mu naught, the magnetic constant, which is equal to 4 pi times 10 to the negative 7 henries per meter, times small n, which we've established is 1100 turns, divided by 0.95 meters, and then times the current, which is 3.50 amperes. So if we put this into our calculator, we're going to find a magnetic field of about 0.005093 teslas. So this is the answer that we get. If you want to write this in scientific notation, you could bring the decimal point three spots over. and write it as 5.093 times 10 to the negative 3 Teslas. Either way works, but either way, that is a pretty nice and basic example of a problem involving this solenoid equation. And notice that nowhere in our solution did we use the radius of the solenoid given in the problem. That was a bit of a red herring, because remember, in our initial explanation of what a solenoid was, the radius is negligible because of how long the solenoid is. So this detail is red herring, completely irrelevant. You only need to worry about the actual values included within the equation. And that was this. So I hope this little example helped you understand it better. And I also hope the derivation helped you out as well. If you have any questions, please leave a comment down below and I'll do my best to help you out. Or if you have requests for future concepts you'd like me to cover, I'm always welcoming suggestions for that as well. So that is all for this video, and I hope you have a lovely day. Bye-bye.